we did the postulates of the valence bond theory. Valence bond theory, which talks about the formation of a covalent bond, and we learned the various postulates of the valence bond theory. But out of those postulates which was given by the valence bond theory, the certain postulates were certain postulates was not true in all the cases. So we have the limitations of valence bond theory. What was the postulates of valence bond theory? The postulates was that half-filled orbitals should overlap with each other. The two atoms, if their two atoms want to form a covalent bond, then their half-filled orbitals should overlap with each other with the opposite electron spin. Then second limitation, postulates was that if the two half-filled orbitals which are coming closer for the overlapping, they should have approximately same energy. The number of bond formed by an atom is equal to the number of half-filled orbitals. The extent of overlapping decide the strength of a bond. The geometry of the molecule is decided by the overlapping of the orbital, in which direction the orbitals are overlapping. So these was the certain postulates which was given by the valence bond theory. But as I said, the valence bond theory have some limitation. The limitation number one, the valence bond theory says that the number of bond formed by an atom is equal to the number of half-filled orbital. But later we come to know that this statement is not true in all the cases. Now let's see for certain elements where the statement is true. That is, the number of bond formed by an atom is equal to number of half-filled orbital. This statement becomes the first limitation. For example, suppose if I have an atom like nitrogen whose atomic number is 7, so if I'm writing its electronic configuration will be 1s2, 2s2 and 2p3. So 2s2 outermost shell configuration and 2p3, so 2p3 means 1 electron. So I can say that in the case of nitrogen there is a 3 half-filled orbital, and if there is a 3 half-filled orbital, so according to valence bond theory the nitrogen will form 3 bonds, which is true also. The nitrogen generally form a 3 bonds only, like NH3 I can say. The valency of nitrogen is 3 only. Oxygen, suppose if I am considering whose atomic number is 8 and its electronic configuration is 1s2, 2s2 to p4. If its outermost shell configuration is 2s2 and 2p4, so there is a 4 electron in the outermost shell. So 1, 2, 3 and then pairing will take place. Now in the case of oxygen, I can say that there is a 2 half-filled orbital. So according to valence bond theory, the oxygen will form 2 bonds, and it is true also because oxygen form a molecule like H2O, where oxygen combines with the 2 hydrogen. Then next element, let's see, that is carbon. We have atomic number is 6, configuration 1s2, 2s2 to p2. 2 electron in the outermost or in 2s orbital and 2p2, that means 2 electron in the p orbital. This is the outermost shell configuration. I am writing only the outermost shell, the electrons for the outermost shell configuration, because we all know that in a bonding only the electron present in outermost shell takes part. So here I can say that there is a 2 electron in the outermost orbit. So how many half-filled orbital? Then I can say there is only 2 half-filled orbital, these two. This is completely filled. So according to valence bond theory, this will not take part in a bonding because it is a completely filled. So the bonding will be done by only these 2 electrons. So according to valence bond theory, the carbon should form 2 bonds. But the truth is that the carbon always form 4 bonds. In organic chemistry, always it has been said by the teacher that always count the number of bonds formed by an atom, that it should be always 4. So here the valence bond theory failed. It failed to explain that if the carbon is having only 2 half-filled orbital, then how it is forming 4 bonds. Example, I can say in methane, carbon combines with the 4 bonds. So according to valence bond theory, carbon will combine with the 4 hydrogen only if it is having 4 half-filled orbital, which is not here, which is not present in this case. So the limitation in the case of carbon. Similarly, if I am considering boron, whose atomic number is 5 and its electronic configuration, I can write 1s2, 2s2 to p1, that is total 5 electron. So here 2s2, that is 2 electron in s, and p have only 1 electron. So how many half-filled orbital in this case? I can say that half-filled orbital, there is only 1 half-filled orbital. So according to valence bond theory, the boron should form single bond, but at the same time I can say that boron is considered as a trivalent atom. Trivalent atom means its a valency is 3, and boron always combine with the 3 elements. The example I can say BF3. In BF3 the boron combines with the 3 fluorine atom by the 3 bonds. Then after, so in the case of boron, again I can say the valence bond theory failed to explain that if the boron is having only one half-filled orbital, then how it is forming 3 bonds. After boron, the next is beryllium, whose atomic number is 4. So its electronic configuration is going to be 1s2, 2s2, and if it is 1s2, 2s2, that is outermost shell configuration is 2s2. And 2s2, that means it should have 2 electron in the, if I'm talking about the number of half-filled orbital. So here the number of half-filled orbital is 0. There is a no half-filled orbital. And if there is a no half-filled orbital, then according to valence bond theory, the beryllium will not form any covalent bond. And that means the beryllium will remain in the free elemental state. But we know that the beryllium is forming 2 bonds with the fluorine. BeF2 we are having. We have BeCl2, BeH2. So beryllium forms 2 bonds. So how it is forming 2 bonds? Even when it is not having any half-filled orbital, is not explained by the valence bond theory. So this again becomes a limitation of valence bond theory. So this was the first limitation of valence bond theory, that in many cases the number of bond formed by an atom is not equal to the number of half-filled orbital. Now let's see the second limitation. The second limitation of the valence bond theory is with respect to the geometry of a molecule. The second limitation is with respect to the geometry of molecule. According to valence bond theory, the geometry of a molecule is decided by the overlapping of the orbitals, means in which direction those orbitals are overlapping. That decide the geometry of a molecule. So let's see the geometry of what ammonia molecule first. Now here in the case of ammonia, we have the configuration of, in case of ammonia, that is NH3, which contain nitrogen and hydrogen. So we have a configuration for nitrogen which have 3 half-filled orbital. Means I can say that from the nitrogen who will come for the bonding, then simply I can say that from nitrogen the p orbital will come for the bonding. And so if p orbital from the nitrogen, p orbital, that is jumble shape, okay, each one, this is px, this is py, and this is pz, x-axis, y-axis, and this is z-axis. This is having single electron, this also have single, and this also have single electron. Now see, when I'm saying it's an ammonia molecule, that is NH3, px, py, pz, that we know that px, py is the pz axis. This is xy and this is z axis. And we know that the angle between them is 90, 90 and 90 degree. That means the angle between all axes is 90 degree. That this is x, this is y, this is z. Or I can say this is x, this is y, this is z. Okay, so all are 90 degree. In this case, what we had done, we had just plotted this. We had drawn the opposite line also. That is this one, and this one. So if I'm talking about the angle between these two, again I will say the angle between these two will be the 90 only, because this is now it's a 3-dimensional axis which has been plotted on a 2-dimensional board. So I can say that in this case, so it's like I can say for this line is like, these are the 2 angles, and this line is coming out towards me, and that line is moving on the back side, that is towards that side. So this is coming towards me, that means again it will make a 90 degree like this, and this line is moving towards you, that means that line, that will also make the angle of 90 degree. Similarly, this line will also make a 90 degree, that means they are something like this. First I draw like this one, so it's a 90-90. Then I'm drawing the same thing like this. So again it is angle is 90-90, 90-90. And the third angle which we are having, it is like this. So again it is a 90 only. So here all x, y and z axes are making an angle of 90 degrees. So here I can say the angle between y and z axis, that is these two, 90 degree. X and y, these two 90 degree, 90 degree, 90 degree, 90 degree. Don't consider it's going to be a 45 degree, because here we are drawing the 3-dimensional things on a 2-dimensional figure, 2-dimensional board. Okay, now it combines with the hydrogen. So hydrogen will come. hydrogen which is a spherical in shape, with opposite spin it will come, and what structure will form? Let's see. So during the overlapping, I can say that in this case, this is the first, the opposite side will get smaller, because as I said, during the overlapping, the whole energy gets concentrated on the overlapping side, so opposite part gets smaller. The second one, the third one. The first hydrogen will overlap here. The second hydrogen will overlap here. The third hydrogen will overlap in this case. So ultimately we got an ammonia molecule. This is the ammonia molecule according to the valence bond theory. But question arises that is it correct? So let's see if I'm talking about the angle of this axis of each. So this is the axis of this angle. This is the axis of this angle. This is the axis of this angle. So here the angle between these two. This is H and H. So here I can say that angle between hydrogen, nitrogen and hydrogen. It is going to be, since it is x-axis, y-axis and z-axis. That means I'm talking about the angle between these two. Right. So as I said, this angle is going to be 90 degree. So according to the valence bond theory, the H and H bond angle in ammonia should be 90 degree. But when it is calculated experimentally by the X-ray spectroscopy and all method, then we come to know that in case of H and H, in case of ammonia, the H and H bond angle is not 90 degree. Instead, it is 107 degree 18 minutes. This is the actual bond angle of the ammonia molecule. While in case of valence bond theory, if I'm using a valence bond theory, then this will be the geometry of ammonia and the bond angle should be 107 degree, bond angle should be 90 degree according to valence bond theory. But actually it is how much? 107 degree 18 minutes. Now in case of, suppose the second example I'm considering water. In case of water that is H2O. So the oxygen is going to be a central atom. This is the oxygen having only two half-filled orbital. So in case of oxygen, I can say this orbital will be already completely filled. Combining with the two hydrogen atom, in case of ammonia it was 3. So then two half-filled orbitals. So I can say this here no bond formation because it is already paired. Now I'm talking about water molecule. So in case of water, this will not take part in a bonding and this will be full form. Now in the case of this H, this will be O and this will be H. So again I can say that in this case also HOH bond angle should be equal to 90 degree according to valence bond theory. But we come to know that in case of water molecule, HOH bond angle is not 90 degree. Instead it is 104 degree 35 minutes. So why it is 104 degree 35 minutes and not the 90 degree is not explained by the valence bond theory. And if the bond angle is different, it means the actual geometry of the water molecule in which the angle is 104 degree 35 minutes is totally different from this geometry. So in certain cases I can say that valence bond theory failed to explain the geometry of a molecule also. So now this becomes a limitation. These were the main two limitations of the valence bond theory. And after the failure of the valence bond theory, the need of hybridization comes. That means after that, to see, once I come to know that the carbon is forming only 4 bonds while it have 2 half-filled orbital, why this is forming 3 bonds if there is only 1 half-filled orbital, why the geometry is different, why the bond angle is not 90 degree. In case of ammonia and water, why it is 107 degree 18 minutes or 104 degree 35 minutes. So to answer all the things we require some, so we just wanted the answer for all these queries. So to answer all these queries, we introduce a new concept and that is called as a hybridization concept. So hybridization concept comes into the picture only after the limitation of the valence bond theory. So if I'm asking what is the need of hybridization, then these are the two reasons. That is, in certain cases, in these two cases, the valence bond theory fails. That's why we require this hybridization concept.